Okay. Delta U is change in internal energy. We know that. Q stands for heat, and W stands for work. Now, we use signs, positive and negative, to indicate the direction of the flow of energy. Recall that the system is the part of the universe of interest to us. The system is what we're interested in. So the system is always going to be the balanced chemical equation. For example, like if you're talking about the combustion of methane, and that's not balanced. There we go. That is the system. The CH4, the O2, the CO2, and the water. Now, what that's happening in, that reaction's happening in an environment, in a vessel. So, and maybe you're standing by that reaction. So everything else that you don't see there, like you or the vessel it's in, that is the surroundings. So the system's the part of the universe that's of interest to us. It's the balanced chemical equation. Now, why it's important to understand all this is because all this tells you whether the values are positive or negative. So the way chemical reactions transfer energy is in the form of heat and work. Anytime heat goes into the system, that's positive. Anytime work is done on the system, that's positive. Now, if it's being done on the system, it's coming from the surroundings. Okay, so the surroundings is losing it. That is the first law of thermodynamics, what we're doing here. That the heat absorbed by the system, it's going to be equal to the heat released by the surrounding. And the word absorb, that's what that positive is taken care of. And when I say the word released, that's what that negative is taken care of. When we're working this formula, 9 times out of 10, it's always about the system. So, for example, calculate the change in internal energy, and I'm going to abbreviate that, of a system that absorbs 70 kilojoules of, heat while doing 30 kilojoules of work. Okay, and you've probably seen me work some like this, maybe in the lectures, but the formula is always delta U is equal to Q plus W. That's always the formula. We can clearly see that the Q is 70 and the W is 30. But we have to read the context of the question to see whether the Q and the W are positive or negative. Okay, so look at the Q. It says system absorbs. The system's what we're interested in. So if the system is absorbing it, that's positive. So see, that means your Q is going to be a positive 70 kilojoules. And typically, when we're learning to do this math, if it's positive, we don't write positive in front of it. We just leave it alone and it's understood. Okay, so that's that part of the equation. Plus, the W, it says, is 30, but what is the system doing about this work? It's doing it. It's not absorbing the work. The system is doing the work. That tells us that the W is negative, so it's plus a negative 30 kilojoules. That's why sometimes the formula looks like delta U is equal to Q plus W, and sometimes it looks like delta U is equal to Q minus W. Because look what happens here when you condense it, right? I mean, math, 70 minus 30 is what it is. But the formula is always Q plus W. Whether it's positive or negative depends on the context of the question. So the answer here is 40 kilojoules. And let's talk a little bit more about that to understand what it's saying. Because the change in internal energy of a system technically this is labeled a system, is positive 40 kilojoules. That means when whatever process is happening here, when this chemical process is finished, the system has 40 kilojoules energy more at the end of this process than it had when it started. Okay, the system has absorbed that much energy. Where did it get that energy from? It got the energy from the surroundings. First law of thermodynamics says energy is not created nor destroyed, but is transferred from one form to the other. So if the system now has 40 kilojoules of energy more, that means the surroundings, you, the air, the vessel, whatever else, now has 40 kilojoules of energy less. That means that the change in internal energy of the universe is zero. Because if the system's positive 40 and the surroundings is negative 40, the change in internal energy of the universe will always be zero. This is the first law of thermodynamics. Okay, it's just being shown mathematically. And that takes care of two of the questions I had about the formula, Q and W, and understanding whether the Q and the W are positive or negative. Okay, this concept is covered more in your book. It starts on page 193 in your book, but there's a table 5.1 on page 194, that it goes over the Q and the W and when it's positive and when it's negative, and that might help, but of course I don't think it's a good idea ever to memorize stuff. I guess some stuff you have to, but if you can understand it, it makes things a whole lot easier to learn. But where I always go to is kind of where I started with the lecture, of understanding the difference between the system and the surroundings. And if the system is what I'm interested in, then anytime something happens to the system, heat goes into it or work is done on it, that's a positive thing, because system's what I'm interested in. Okay, let me find the next question, number 8 on chapter 5, connect. Number 8 on chapter 5, connect. Okay, so number 8 on chapter 5, connect, is like a reverse combustion equation. I'm going to leave the states off just for time's sake of writing it. So it's the reverse of glucose combustion. I ran out of room. But the change in enthalpy for this is a positive 2,803 kilojoules per mole. Okay, now, here's the way that works. The positive 2,803 kilojoules per mole, it means per mole as written in this equation. Okay? So that means if there's 6 moles of carbon dioxide reacting with 6 moles of water to produce 1 mole of glucose and 6 moles of oxygen. Now, what would happen, you think, if I change this and I had 12 carbon dioxides, 12 waters? See, in order to keep it balanced, I'm going to have 2 glucoses and 12 oxygens, because you can't just like double one of them. The whole equation has to stay balanced. As written, if it was 6, 6, 1, and 6, if those coefficients absorbed 2,803 kilojoules, then what would happen if you doubled all the coefficients? Well, it would double the kilojoules of heat that it absorbs. So what is that, 5,606? Is that right? If you double the coefficients, you double the enthalpy change. Okay, so it's important to understand that when you're given, this is called a balanced thermochemical equation. It is as written. And so the question is asking about the grams of oxygen. And it says, in my example, we all have different numbers on our connect. Again, this is chapter 5 connect, number 8. But mine says, if I've got 21,200 kilojoules of energy consumed, the question says consumed, Therefore, I know this is positive, okay? If it says 21,200 kilojoules of energy released, then I would know that's a negative. Okay, so the balanced equation, I know I'm relating it to oxygen because that's what Connect asks about, the oxygen. And the balanced equation says, well, it consumes 2,803 kilojoules for every 6 moles of oxygen. Okay, now how did I know to write it that way and not the 2803 on top and 6 on bottom? I know that not everybody has a question about that, but in case you do, it's because I need the kilojoules to cancel. And then finally, the question says calculate the mass. So I know I want my final answer in grams. So how are moles of O2 and grams of O2 related? Well, a mole of O2 is 32 grams because it's O2. Okay, so again, when you're given a balanced thermochemical equation, it's always whatever the coefficient is as it's written. Then I had another, number 10 and 11. Okay, 10 and 11 are Hess's law questions. Have you watched videos on Hess's law? So let me take a picture of them so I don't have to write them. Okay. So here's number 10. Now, what we're doing in number 10, this is Hess's law, is these equations up here that we have the delta H for. These are our puzzle pieces. We have to make these fit together and add up so that they look like this one at the bottom. Okay? Now, assuming you've watched a Hess's law video, I'm not going to assume that. Let me pretend that maybe you don't know anything about Hess's law, okay? So I'm going to come back to this in a second. Look, if A makes B, and the delta H for that is 10 kilojoules, and B makes C, and the delta H for that is 20 kilojoules, then if I added these two equations together, it's just like algebra. If you have the same thing on both sides of the equation, that can cancel out. And so see, when I add these together, they add up to be A makes C. I still use both of them because technically what I had before I cancel the B's out is I had A plus B makes B plus C. And so in summary, A just made C. Okay, but it still took both equations. The delta H for A to make C is 30 kilojoules because if you're adding these equations together, you just add the delta H's together. Okay, now the same thing goes like I was saying earlier. If A makes C is 30 kilojoules, then what if I need 2 A's making 2 C's? What would that be? Well, that would be 60 kilojoules. What if I wanted to know what's the delta H for C making A? Well, if A makes C is 30, then if I reverse that and have C making A, then the delta H is negative 30. Okay, so we have to keep all this in mind because this is how we make our puzzle pieces stick together. So going back to number 10, Hess's law. This equation at the bottom, imagine this is what I want when I put my puzzle together, this is what I want it to look like, okay? So, I want 2 NO2s on the reactant side of the equation. Now look at the pieces above. Where's NO2? The only place you see NO2 is right here, okay? In the pieces above, it's on the product side. So I know I've got to flip this whole equation around. The whole thing has to be flipped. How do I know I have to flip it? Because look, I want the NO2s on the reactant side. So I'm going to try to erase all those little circles and lines I've got. And I'm going to flip that equation around. So when I flip it around, I'm going to have the NO2 and the O2 over here. And again, I'm leaving states off because I know that's everything's a gas. And I'm just leaving them off so I don't get a whole bunch of junk that confuses me written down. Okay? And then I'm going to put the NO and the O3 over here. Do you see I flipped the entire equation? You can't just move the NO2 over. You have to flip the whole equation. It still has to stay a balanced equation. Why did I flip it? Because I wanted, when I added them together, I wanted the NO2 on the left side, on the reactant side. Now, when you flip an equation around, what does that do to the delta H? It changes the sign. So it's no longer negative, it's positive. Okay, now I'm going to mark through the one that I was given originally because I don't have that anymore. I've flipped that one around. Okay, is that all that I needed to do to the NO2? See, I moved it. I wanted it on the reactant side. What else is different about it? It's got a 2 in front of it. Okay, so can I just put a 2 in front of it? You have to keep the equation balanced. If you're going to double the NO2, then what do you have to do to the oxygen? You have to double it. What do you have to do to the NO? You have to double it. What do you have to do to the ozone? You have to double it. If you tripled it, you'd have to triple everything all the way across. If you cut it in half, you would have to half everything all the way across. Okay, so 198.9 also has to be doubled. And so it's still going to stay positive because changing the coefficients doesn't change the sign. It just changes the quantitative value. So that's a positive 397.8 kilojoules per mole. And now I'm going to mark through this one because I don't have that one anymore. I've doubled it. Okay. Now, what else needs to be changed about this one? I also see, sometimes it's hard to see the second step, and it just takes practice doing them, okay? What I see, the ozone is O3, okay? When I look up here, do I want O3 in my final equation? No, I don't want O3 in the final equation at all. So I know that I've got to get the O3s to cancel. Well, what do you mean by cancel? I'm going to change slides. See over here when we cancel the B's? If you get them on opposite sides, they'll cancel. So here in the equation I'm working, I know I need the ozones to cancel out. Where are the ozones? Here and here. In order for them to cancel, they have to be on opposite sides. Okay, so these are on opposite sides, but the problem is there's 2 of them here and there's only 1 of them here. So it's just like in algebra. If you have a 2x and an x, you can only cancel out one of the x's, right? You can't cancel out both of them. So I need the coefficients to match. That tells me that I need to double this one. I know I don't need to change this 2 because the whole reason I did that is so my NO2 would be fine. Okay, so I'm going to double this second equation. So if there's a 1 here in front of the ozone, that becomes 2. 3 halves becomes 6 halves, which is 3, right? Because 3 halves doubled is 3. And then what do I do to this one? I double the equation. I need to double that. It's not going to change the sign. It's still going to be negative because I didn't flip it. Negative 284.6 kilojoules per mole. And I'm going to get rid of that one. Okay. Now, I can see, and this is kind of a tricky one that Connect throws at us. I didn't use this one at all. That little monoatomic O, that just plain old O, I don't want it showing up down here. It doesn't cancel with either of the two equations above it. So actually, I'm not going to use that one. That's just like extra information that I don't need. Like a lot of chemistry problems, will say, calculate the density, at a certain temperature. You actually don't have to have the temperature to calculate the density. Okay, it's just extra information. It will change with density changes with temperature, but it's just you got to cull that information out. So, what cancels here? What's the same on both sides of the equation? You got two ozones. Reactant, product. Those cancels. Okay, look at the oxygens. You got 2 of them here and 3 of them here. If you subtract 2 oxygens from both sides, all of these are gone. And on this one, if you've got 3 and you subtract 2, you'll be left with 1. Okay, so just leave 1 there. And now look at what's left. 2 NO2s yields 2 NOs and an oxygen. These top 2 equations will add up to be what you wanted. So how do you get the delta H? You simply add these 2 numbers, a positive 397.8 and a negative 284.6. Okay, that's number 10 on the Chapter 5 Connect. Number 11, it's the same concept. It's a Hess's Law concept. Okay, and I'm going to leave number 11 for you to try to figure out. I'm going to look in the book. I know I have some videos on Hess's Law that you can watch and practice, but Hess's Law is section 5.5 in your book, and it starts on page 210. And I think that is... Okay. Let me know how that works.